Good evening, ladies and gentlemen, and a very warm welcome from the Society of Chemical Industry to tonight's talk from Professor Hayley Fowler on climate change, increasing extreme weather and impacts on water resources. Now, I would say if there's one thing that binds us all together here tonight, it's that you don't want to sit there listening to me talk with a huge long introduction. So I will be as brief as I can, but there are certain things that I am compelled to say by way of filling in this bit of time. The first of which is we're not expecting any fire alarms, and believe me, if there is a fire alarm, you will know about it. So please leave resourcefully and carefully through this door or that door and follow the green and white signs. The second point is that if you have a mobile phone, now is a really good moment to switch it off. The Society is a multidisciplinary forum that goes with the strapline of where science meets business. And it was instituted in 1881 by a royal charter with a group of industrialists, entrepreneurs and scientists to be a forum for the discussion of the most important drivers of society of the day. And I would argue that climate change probably occupies that niche now of the single most important societal driver that we have, even bearing in mind our current UK-related negotiations with our partners in other countries, which I don't want to go into. So I would say it's very well placed with its various local groups and special interest groups to bring people together to discuss climate change now. And I couldn't ask for anybody better to introduce than Professor Fowler here, who I know her from her work as Professor at Newcastle University. She is a Fellow of the American Geophysical Union, as well as being a Wolfson Research Fellow at the Royal Society. Those may seem quite highbrow things to say. What most of you may well know is the International Panel on Climate Change reports, and Hayley will be a contributing author on the 6th edition of that, as well as in the UK Committee on Climate Change Risk Assessment, the next upcoming report from there. A lot of very well respected and internationally renowned research on flood prediction and drought prediction and the risk associated with that, and perhaps most importantly forms a kind of bridge between the people who are doing the science of making these projections of how life will be in the future and the people who will be having to respond to that either through adaptation or mitigation. And so you can expect a lot of science in tonight's talk. You can expect a lot of science about what the impacts of climate change are currently, what they will be in the impending years. So that's more of a definition of the problem, but also science that leads to response, science that leads to policy and the need for action. And maybe, if we're lucky, we'll end up with a sense of cautious optimism, that if we take the right actions in the right way soon enough, maybe, just maybe, we will avoid the worst of the impacts that might take place. So I will invite questions after the main talk, so we will have some microphones to circulate around. So please hold any questions you do have for then, and I will do my best to take as many questions from the floor as we can in the time available. But for now, I would like you to warmly welcome to the stage Professor Hayley Fowler.
I was going to start by saying myself and James were both at the lobby today in Parliament. The time is now. I don't know how many of you heard about this. And we ended up talking to our MP about how we might start to reduce carbon emissions and how do we actually get the government to listen to the public and to actually start to change the way, to bring in policies to actually start to reduce carbon emissions. And I'll say a little bit more about that towards the end of the talk. But I think there's a lot of rhetoric around climate change at the moment within the government, but there's perhaps not very much action. So we really need to be thinking about how do we actually lobby Parliament to get them to start to take action and to provide things like subsidies for renewables, to basically really think about things like Heathrow expansion, etc., etc. So, I mean, the reason that I'm concerned about climate change, and I've been working on climate change now for about 20 years, and working on extreme weather as well and water resources for most of that time. You've probably all seen this quite iconic image here, and in fact you may have tweeted or posted something on Facebook last Friday, which was Show Your Stripes Day, and you can now go onto the website and you can get you can produce these type of stripes for anywhere in the world, really, any country in the world, certainly in some US states, etc. But this shows the change in global temperatures from 1850 to 2018, and you can see just from this, and okay, that's quite a short time period, but it's the time period since the Industrial Revolution, since we've been emitting huge amounts of carbon dioxide into the atmosphere. And you can see that this basically is quite starkly showing us the change in global mean temperature. So some of those more observant among you will also notice that I'm wearing my science, and this always causes a talking point, but this is exactly the same thing, and actually this only goes up to 2017 because I bought it last year and they hadn't yet obviously released the warming, the global temperature for 2018. But basically, you know, this is what we're talking about. We're talking about a large amount of warming already. So since pre-industrial times, we've already seen a degree of warming globally. And I'll tell you a little bit more in a moment, but there's a lot of impacts already that we're seeing from this warming globally. And of course, the warming's not equal across the globe. We're seeing bigger warming in some areas than others. And at the current rate, we're going to reach this first target that was set by the Paris Agreement, the 1.5 degree warming, between 2030 and 2052. That's the information that came out of the special report on global warming of 1.5 degrees by the Intergovernmental Panel on Climate Change. The good news is that past emissions alone do not commit the world to 1.5 degrees yet, but they will do very soon. And I just wanted to show you, this is an updated spiral diagram by Professor Ed Hawkins, who is quite well known now for these visualizations of climate change. And this is really showing global temperatures from, again, 1850 to 2018, but it's also showing these Paris Agreement targets. And you can see how close we already are to that 1.5 degree target there. And actually, if I play it again, it's playing again anyway, great, then you can see as well how actually the warming has speeded up quite dramatically since the 1980s or so. If you watch this, it suddenly billows out there. And that's because we're emitting ever increasing amounts of carbon dioxide and other greenhouse gases into the atmosphere. We would actually be at 1.5 degrees warming already if it wasn't for air pollution. So we can actually thank Asia and some of these big cities in the developing world for these aerosols, because actually without that we would almost certainly be at 1.5 degrees of warming already. So one of the ironies of I suppose, cleaning up our cities is that actually we will see more warming as a result of that. But it doesn't mean we shouldn't clean up our cities. We have to be thinking about doing both. So I'm just showing here some of the impacts, potential impacts, or they're actually real impacts that have happened already of living in a 1 degree warmer world. So we're living in this 1 degree warmer world now, and these are some of the impacts that we're starting to see. You can see here the Rhine in Germany last year, for example. The river got so low that it was no longer navigable by boats. We had big air pollution incidents in Canada, in some of the cities there. Flooding, we've had flood events all over the world. I mean, we had a flash flood event just 2 days ago, or was it even yesterday, in Stirling and Edinburgh, which probably didn't make the news down here, but it was there were people swimming in the streets in Stirling. Well, obviously that's even more dramatic flooding, and obviously heat wave events as well are increasing. And you can see how dramatically some of these impacts can take place here. These are satellite photographs from the summer last year, and you can see that between June the 30th and July the 19th, you saw this very very severe drying basically over northern Europe here. And you can see here, this is the Europe land temperature anomalies from 1910 up to last year, and it's the anomaly from 1961 to 90, so about this period here. And you can see really this very dramatic increase in temperature anomalies, and this isn't just looking at heat wave, this is looking at the average over April to July. So you're talking about sustained high temperatures over quite a long period here, and you can see that 2018 event there. Of course, there is heat wave predicted for France and quite a lot of Central Europe in the next few days as well, which is expected to break records across Europe in terms of temperatures. So we're seeing a lot of these record-breaking events, and that doesn't happen by chance. When you roll a dice, you know, you get a 6, 1/6 of the time. These record-breaking events, to get basically record-breaking events year after year after year, means we're no longer living in a stationary climate. We're seeing this warming effect. Another thing that you've probably seen in the news is that India's 6th biggest city has just run out of water. Now that's crazy, isn't it? You know, I mean, basically, if you remember, Cape Town almost ran out of water last year. They were 3 days away, something like that, from actually running out of water. Oh, hang on. I was expecting that to play the GIF, but it doesn't seem to be working. That was working earlier on. Let's see. Mouse. No. I don't know. That GIF basically shows the reduction of water in the reservoir, but it doesn't seem to be working. I can't get the mouse to work either, so I can't show you that, sorry. But basically you can see this is not just climate change, obviously, but it's a failure of the authorities to actually manage the water resources adequately. It's a failure of the monsoon as well. So the monsoon is a month late almost now in India this year, and they're expecting it, but it still hasn't happened. And it's also to do with increasing population pressures in this city. So the population has grown and grown and grown and grown, and because of that, they've extracted more and more and more groundwater, so water under the ground, which has reduced the water table significantly. And it also hasn't rained for 200 days. So, you know, we can be expecting, though, to see more of these type of things happening. There are actually 6 cities in India at the moment that are really very short of water. This one has run out. So the other thing that scientists are able to do now is something called event attribution, which you may have heard about. And actually, we're living in a 1 degree warmer world, and we can actually look at how much that warming has contributed to the intensity or the frequency of particular types of events. And some colleagues in the United States actually looked at the effects of global warming on Hurricane Harvey. If you remember, record rainfall over Houston. You can see here that basically, you were seeing 800 millimeters of rainfall over a very large area of the city. And I don't know whether you all remember the huge floods that ensued from this rainfall. Basically, they can run a kind of world that would have been. They take away the global warming signal and they run their computer models, and they also run the models for the world that's now, and they look at the difference between the two. And they basically found that the global warming intensified the rainfall associated with Hurricane Harvey and also made stalling more likely over the city. And there's also been some really interesting research published quite recently that basically shows that actually this almost the roughness, if you imagine the city's kind of, these big buildings in the city are kind of poking up into the atmosphere, and as the hurricane comes along, it stalls over the city because of these buildings, basically. So the roughness is actually capturing almost the hurricane and stopping it over the city. So it's not just warming, it's basically all of these other things, but they're all anthropogenic, they're all human-induced factors. So because we're building these cities higher and higher, we produce more of this roughness effect as well. It's all very interesting. So yeah, I'd argue that we're already experiencing extreme events. We've always experienced extreme events, actually, even before warming, but we're actually experiencing a lot more of these now. So before moving on, I just wanted to say something about the greenhouse effect. And I think that probably most of you know a little bit at least about what the greenhouse effect is. But basically what happens is that the solar radiation, the shortwave radiation, comes from the sun and it goes through the Earth's atmosphere, and some of it's reflected back straight away by clouds. And then some of it will come, most of it in fact comes through and it hits the Earth's surface, and it basically is re-emitted by the Earth's surface as long-wave radiation. Now there's a special type of gas that has the right, basically is able to absorb what these wavelengths of a certain frequency, basically, and it can actually absorb this radiation as it comes back from the Earth's surface. And these are called greenhouse gases. And so carbon dioxide is one of the major ones. And so we actually need the greenhouse effect to keep the Earth warm. If we didn't have any of these greenhouse gases in the atmosphere, we wouldn't be able to live on Earth because it would be too cold. But actually, although the amount of greenhouse gases in the atmosphere is actually quite small in terms of an absolute concentration, they have a very potent effect on the Earth's surface. And then, of course, you then get feedback effects from things like water vapour, for example. As the atmosphere becomes warmer, you get more water vapour, and that itself is a greenhouse gas, which then amplifies that signal. Now, all of this is not rocket science, right? We've known about this for a really, really long time, and I mean, sometimes I find this quite surprising, I suppose, that, you get people like Donald Trump who don't believe that we're warming the Earth's climate. And actually, it's really not very difficult science to show. I could actually have a table here and put some carbon dioxide, increase the carbon dioxide in a container and actually shine a lamp on it and actually show that it heats the air inside, basically, as you increase the carbon dioxide concentrations. We've known about the greenhouse effect for more than 150 years. And actually it was John Tyndall who basically discovered this. And he actually measured these properties, basically this ability to actually capture radiation of a number of different types of gases. And he had a look at what their properties were. And so he found out that, for example, oxygen and nitrogen have quite low ability to capture to capture radiation. But then when you look at carbon dioxide, nitrous oxide and water vapour, they're somewhere about medium ability. Then methane was quite highly potent. Yeah? So methane's a very potent greenhouse gas. They all have different abilities to absorb. And then again, you know, we've known for a very long time as well about the possible response of the climate system to a doubling of carbon dioxide in the atmosphere. So a very clever scientist called Arrhenius, and I'm never sure if I actually pronounced that correctly or not, basically did some calculations in 1896. Now, you know, that's over 100 years ago, and basically calculated, just based on these estimates of carbon dioxide doubling in the atmosphere, that a doubling of carbon dioxide would raise surface temperatures by about 5 to 6 degrees. We now call this climate system's response to a doubling of carbon dioxide the equilibrium climate sensitivity. And actually, you know, his estimates in 1896 are really not too dissimilar from the Intergovernmental Panel on Climate Change estimates in 2013 in their 5th assessment report, you know. So really this is something that can be proven very simply. You know, we are warming the atmosphere. And actually, you can see here that in May 2019, which was the latest measurements, atmospheric carbon dioxide is higher than in the last 600,000 years. That probably won't come as a surprise. And it's at about 415 parts per million. And you can see here the carbon dioxide concentrations in the atmosphere from 400,000 years ago to the present day. And this very dramatic rise, basically, since the Industrial Revolution, and particularly in the last 30 years or so. And really it's becoming an exponential rise in carbon dioxide in the atmosphere. And you know, you can see here on this red line, this is where we measure the carbon dioxide on Mauna Loa in Hawaii. And you can see basically this seasonality, this little sort of saw shape, is basically to do with the most of the landmass in the Earth is in the northern hemisphere. And so basically when you get the greening of the northern hemisphere during the summer, the trees take up, or yeah, basically the trees take up a lot of carbon dioxide, and then you obviously get that release again. It increases again during the winter. As a result of this, you also get more acidity in the ocean, as well as the ocean also takes up more carbon dioxide itself. And I thought this was quite telling, really. So, I mean, maybe we shouldn't be surprised by this, because we're seeing an exponential increase in greenhouse gas emissions and carbon dioxide. But actually, if you look here, I was quite staggered to see that I'm about here, so I'm 44. So basically, 70% of global fossil fuel emissions have occurred in my lifetime. That's pretty scary, isn't it? Yeah, I was quite, yeah, I mean, it's not surprising, but actually if you start to look at the numbers, it starts to become even more worrying. And I've said already that not all of these gases have the same effect. And you can see, actually, it's not just, though, this ability, gone forwards. It's not just this ability to absorb radiation that matters. So actually, you know, something like methane has a greater ability to absorb radiation, but it's also the amount emitted that matters. And that is why carbon dioxide is the most potent greenhouse gas. Because although it's not, it basically, because of the amount of carbon dioxide we actually emit into the atmosphere. And you can see here this cooling effect of sulfate aerosols, and that's what also causes acid rain. So, I mean, I wanted to quickly explain, I suppose, where the Paris Agreement targets came from. So, part of the 5th assessment report from the Intergovernmental Panel on Climate Change looked at the link between basically global temperature change and the cumulative carbon dioxide emissions from 1870, and basically found that there is a direct link between these two things. So there's a direct link between the amount of carbon dioxide we put into the atmosphere and this temperature response. And we knew this already, but actually it's quite a linear response, as you can see here. So actually we can start to link what global temperature we want to get to by providing an emissions target, and that's why they were able to come up with these emissions targets for these 1.5 and 2 degree temperatures. And so in Paris, they obviously came up with 2 degrees. Basically, they're going to try and hold the increase in the global average temperature to well below 2 degrees above pre-industrial levels, and to pursue efforts to limit the temperature increase to 1.5 degree above pre-industrial levels. And the reason they chose these levels is because there's been a lot of work in climate change science and impacts over the years that's looked at these thresholds, and basically above 2 degrees, it's believed that there potentially are tipping points that actually will be reached in the climate system, and we may provide, for example, large feedbacks with methane release and positive feedbacks with that, or other tipping points basically that we might reach. So we can't guarantee, certainly in our models, that we won't see some of these things above 2 degrees. So we think there's potentially dangerous thresholds above 2 degrees. And that led to basically this special report on global warming, which came out at the end of last year, which basically looked at how we could actually achieve some of these targets for the Paris Agreement. They came up with a load of different ways that we could actually achieve the 1.5 degree and 2 degree targets, but they also looked at the difference in impacts between the two scenarios, so if we got to 2 degrees or 1.5 degrees. Oh, again, that's not working. Oh, it is. There we go. So there's a number of, you can see how much effort goes into one of these things. And this is similar for, I mean, it's probably even bigger actually, the 6th assessment report at the moment. So there's a huge amount of science that goes into one of these reports. So going back to this, I just wanted to explain a little bit more. Basically, we've got this link between carbon dioxide emissions and global temperatures. And we can see here, for example, this is our 2 degree warming, and it gives us a carbon dioxide total that we can emit. And we can look basically at this and we can say, okay, so if we want to limit warming to 2 degrees C, we need to limit our emissions to less than 1,000 gigatons of carbon. But actually, if we include all of the non-carbon dioxide forcing, actually reduces it even further. And we can do this for both these scenarios. So for 1.5, we'd have to keep it below 615. And then we can look at how much we've already emitted, and there's obviously some uncertainties on this. But we've already emitted quite a lot of carbon actually into the atmosphere. So we're talking about 600 or so. And then we can look at basically, and I think I've written that wrong, but basically we can look at how much carbon dioxide we emit each year. And until last year, actually, we'd really been seeing a plateauing of carbon dioxide emissions over the 4 years before last year. But last year we saw an increase of 2.7% globally again. So although we thought that perhaps we were starting to reach some kind of equilibrium point, I suppose, of emissions, we're actually starting to see this increase again. And actually, this can then tell us how long we've got before we reach the point at which we've emitted, well, basically, so we've got a 50% chance that we've only got 8.9 years, basically, and a 33% chance that we've got 16.5 years. And of course, all of these studies show slightly different numbers, but basically, for 1.5, we really haven't got very long. you know, for 2 degrees we've got a little bit longer, but still not that long actually. We're talking about sort of 30 years or so to really do something. And just to say as well, though, Paris isn't enough at the moment. The Paris Agreement is voluntary and nation-set targets. So they're nationally set and they're voluntary. So basically, they're not legally binding in any way like Kyoto were. So nations don't need to stick to them. And actually, at the moment, they've made these pledges. So they've made pledges to reduce their emissions by a certain amount, by a certain time. And actually, with the Paris pledges, if they're kept to, of course, only takes us to 3 degrees of warming by the end of the century. So even with Paris, we're not going to get to 1.5 or 2. And of course, I said this already, but basically, if we get a 1.5 degree warming, we don't actually see the same amount of warming everywhere and all of the time. Actually, we get a lot more warming over land, basically because of these soil moisture feedbacks. And we also get a lot more warming in the basically the high latitudes of the northern hemisphere, and to a certain extent the high latitudes of the southern hemisphere, because of these snow albedo feedbacks. So as the snow melts, you get more solar radiation absorbed by the ground and less reflected back to space, basically. And actually, I'm not going to take too long over this, but just to show you that actually we see the same linear response of extremes to global warming. So these are the warming temperatures along the bottom here. And then this shows the Mediterranean warming for the warmest day of the year. And you can see that you still get this linear response, but actually it's quite away from the one-to-one line. So actually, for a global warming of, say, 2 degrees, you see an increase of up to 4 degrees in the warmest day of the year in the Mediterranean. You see the same thing, for example, for the minimum temperatures, and actually you see even greater warming of the minimum temperatures, and this shows for the Arctic, for example. That's the one-to-one line there. But again, this linear scaling. And you see the same thing as well for heavy rainfall events, which is something I'm particularly interested in and something that I've been looking at for a number of years now. You see this increase in, this is for the heaviest 5-day rainfall event, you see an increase with warming. So I wanted to explain a little bit about why that would be. Yeah, and then I'm going to tell you a little bit about why we're seeing increases in these type of extreme weather events. It's quite complicated. There's basically a theory called Clausius-Clapeyron, and that states that actually we get, for every degree of warming of the atmosphere, we get about a 7% increase in specific humidity. And actually, so basically you can think about it in simple terms, in the fact that a warmer atmosphere is able to hold more moisture. Yeah? So thinking about this simply, that means that when the atmosphere becomes saturated, that's the point at which it rains, there'll actually be more moisture there to actually rain out. Yeah? And that happens at a rate of about, as I say, 7%. Ooh, again, I've done it wrong. 7% for every degree rise in temperature. And because we get rainfall basically when the atmosphere is saturated, extreme rainfall will increase at about this rate. And actually, I mean, this is a study that I was involved in, but basically we can look globally at all of the different rainfall gauges we have, and we can look at basically what rate we're seeing a change at. And there's been a number of studies that have looked at this now in observations. And you can see that actually, yes, we are seeing about a 6 to 7 degree increase basically per degree warming for daily extreme rainfall. And so therefore you see things like this. And this is showing basically an increase in, you can see it goes from 1910 up to about, I think, 2013 or something. 2008, sorry. That's not actually going to present day. But basically this is looking at one-day extreme precipitation, and you can see that you see this increase basically in the frequency of one-day extreme precipitation over that time. So the thing I've been really interested in the last probably 8 years now or so is what's going to happen though to the type of events that cause flash floods. Yeah, so we really don't know very much about these type of events, and would we expect these to actually become more intense in a warming climate? There certainly seems to be some evidence that actually these type of events scale at a faster rate, and what I mean by that is and these are quite complicated again, but basically we see a higher increase in the intensity of these, a higher rate of increase, sorry, in the intensity of these events with warming, with the, short duration events like hourly events than we see for the daily events. And you can see basically this is showing that it's around 2 times, it can be up to 2 times the rate we see for the daily events. So actually, you know, we might expect these type of events to increase at a much faster rate than these longer duration extremes. So perhaps we'd expect flash floods to increase. And actually, that does seem to be the case in certain parts of the world. So again, I'm talking about things that we're actually observing in now. Yeah, I'm not yet talking about what we expect in the future. This is a paper that one of my postdocs led on, which was published in Nature Climate Change last year. And basically what we did is we looked at changes in rainfall intensities, basically in Australia, over about 150 stations, and we looked at changes between 1966 and 1989, and then looked at sort of nearer to the present day, 1990 to 2013. And it's quite complicated, but basically, if for the 20, we're looking at the 20 top events at each station. For 40, we're looking at the 40 top events at each station, and so on, yeah? So that's relatively simple. And then we're looking at change in magnitude. And this blue line here shows the change over the 150 stations, the mean change, for the daily. And these red dotted lines show basically 1 times Clausius-Clapeyron, which is this 7%, or 2 times, 1.5 times rather, or 2 times. And the grey shading shows basically the effect of natural variability. So what we can see for daily is actually we're seeing a very consistent increase in these daily rainfall intensities, and it's basically what we expect. So we're seeing an increase in line with these theoretical expectations from this relationship, this 7% per degree warming, yeah? But actually for hourly, we're seeing at least a 1.5 times that scaling, and up to 2 times that scaling for the most extreme events. So we're seeing basically 14% increase in these most extreme events for these short duration storms. So this is meaning that these very intense storms that cause flash floods are becoming much more intense at a faster rate. And we can see that in observations in Australia. So some other work that was published by a couple of colleagues over in Australia as well, looking at, you can see this is Australia here, basically looked at how the shape of the storm changes basically with warming. So they took a load of observed data, and they related the shape of the storm to, I'm trying to put this simply, but basically looked at, they basically cut up the storm into these equal bins, if you like, or equal time slots, and then looked at how the storm profile or the shape changed with warmer temperatures. And this is quite interesting as well, because they basically found that at all the stations they looked at, you actually saw more intense peak rainfall. So you see this kind of core of the storm increasing, and then weaker rainfall either side. So you see this intensification basically of the storm as well. And that's quite interesting with warmer temperatures. So it kind of backs up what we're finding with our study. And of course it matters. I mean, it matters for flood risk when you actually have these changes happening. So again, looking at an Australian example, basically if we're looking at changes in extreme rainfall, and then if we look at different seasons, for example, we can see here for summer, we've seen an increase over the whole of the storm durations. In winter, we've seen a decrease. And actually that really matters. So basically, if we see a decrease in the winter, in the intensity of these storms, but perhaps we'll see a decrease in the frequency of those large-scale floods. But if we see an increase in the summer, that of these short-duration storms, we might see much more flooding in smaller catchments and in urban areas. And so the direction of changes, and this is kind of why science is important as well in terms of thinking about what changes we need to make to the way we actually manage rivers and flooding within Australia and the UK. You know, the changes in different seasons really matter to how we actually start to manage these things, because actually they could have quite different impacts in different places. So I want to look a little bit about what might happen in the future. Now this is going back quite a way now, in climate change science terms anyway, so we're going back 8 years. Right, and that's a really long time. So if you want to know stuff about climate change, don't read papers from 2011 because it's really old. Yeah, the science moves on really fast. So this is a paper basically published by a friend of mine, a colleague at the Met Office, Lizzie Kendon, and they used basically relatively high resolution climate models to look at what we can expect in terms of rainfall changes over the UK here, you can see, and basically looked at extreme rainfall in winter, and so we're basically seeing consistent increases, so somewhere between, say, 20% and 40%, up to, say, 80% perhaps. And then they looked at also what we can expect in terms of extreme rainfall changes in summer. And what you can see really there is that we're seeing drying, yeah? So we're seeing no change, or we're not able to tell whether there'll be any significant change, or we're seeing reductions, yeah? So actually you'll have heard this previously, you know, the UK is going to get wetter winters, more extremes, drier summers, more drought, yeah? All good. But actually, the problem with these type of models, and this is something that I've been working on for 8 years now, together with my colleague at the Met Office, the problem with these type of models really is that they can't actually simulate the type of rainfall we're interested in. They can't simulate these summer rainfall events, these short duration, intense thunderstorm type events. And that's simply because they're too coarse, yeah? So each grid cell in one of these very complicated models that's based on physical laws is actually something like 25 kilometres by 25 kilometres, and that would be a high resolution one. Yeah, imagine the size of a thunderstorm. Now, I had a really cool bit of footage actually that I couldn't work out how to get into the presentation, but showing a storm over Canada, and literally it shows this cloud, and you can see water pouring out of the cloud onto this house, right? And that can be the scale of a thunderstorm. Literally, it looks completely unreal, but it is real. From Twitter the other day, somebody sent it to me because they know I'm a bit of a nerd. I'm interested in stuff like this. So, you know, we get thunderstorms that are really quite small. They can be big. You can get really big systems over places like the US called mesoscale convective systems. You may have heard that term used. But certainly in the UK, tend to be quite small. They might even be only a kilometre across or something like that. So basically these models can't actually simulate these type of events. And you can see this here. So this is basically showing our observed records, for an estimate of the winter 10-day, just think of that as an extreme event, but it's basically one that we might expect to happen every 5 years. And this is the model that we're using, the climate model. And you can see actually for winter you're getting pretty good correspondence between those two things. So it's well representing what we expect from observations. But actually in the summer, again this is for a one-day event even, you actually get much higher extremes from the observations than you do from the model. Now the model's just not reproducing those intense events that you get in the summer. So one of the things we've been working on for the last 8 years now is how do we actually quantify what's going to happen to these type of events in the summer, because it's really important, because you know all of our climate scenarios are based on these very coarse resolution models, and they're all telling us that we're going to get drying in the summer, and that might be true, but we need to investigate this further because we know that we can't actually simulate these type of events. And so we had the bright idea, I suppose 8 years ago now, of, you know, actually why can't we use one of these weather forecast models? Yeah, so we've got all of these really cool high resolution models that we use to forecast the weather, right? So that's exactly what we're doing now. And you can see here, this just gives an example of how the model is able to reproduce these type of events. Basically, this is for the Boscastle storm, which some of you might remember, which was an incredibly severe event that happened in the southwest of England in August 2004. And you had this, this is from the radar image, you had this very linear feature of convective cells, basically, which actually moved down the catchment. So actually you just had these thunderstorms moving down the catchment, and this huge amount of water swept through Boscastle and swept away many cars, etc. And you can see here, so this is if we're using weather forecast models. So if we're using a model with 12 kilometre grid cells, you can see we're not really capturing that event. There's some rain there, but 4 kilometres we're starting to capture this event and the intensities of rainfall, but not seeing this convective bands. 1 kilometre though, really doing a very good job of capturing that event. Yeah. So we thought, okay, so weather forecast models can do it. So why can't we run a weather forecast model and force it with greenhouse gases? Yeah. So basically, oh, press the wrong button again. Sorry. So basically, this has started a huge raft of research across the world now. Really. Gosh, okay, 5 minutes to go. I'm nowhere near the end. Sorry. It started a whole raft of work across the world looking at these things. And actually, there's been studies over the US, lots of different parts of Europe, Australia, etc. And actually, they do produce much more realistic extremes. And for that reason, we need them to actually tell us about what's going to happen to future rainfall events in the summer. Yeah, there we go. So this is what it looks like. So these are clouds, basically, in the model, and this is obviously over the US. But you can see how realistic that looks, actually, compared to reality. You can see, for example, the convection initiating off the mountains and moving over the plains, basically, over the night. You can also see a kind of hurricane at some point coming in here. I haven't seen it yet. No, there's something, there you go, see it? So these type of models anyway basically are now included as part of the next set of climate projections in the UK. And actually in the UK it's suggesting that when we use these type of models we still see this drying effect and in autumn as well. But we also see this big increase in short duration events in the summer. And we're expecting these events over 30 millimetres, which is basically when we get a flood warning, to show a 5-fold increase in frequency by 2080. So this is using this type of model. So flash floods will increase. And events also become longer and more intense. So what can we do? So there's basically a couple of things that we need to be doing. We need to be adapting to the changes, because obviously whatever we emit into the atmosphere, carbon dioxide is going to stay there for 100 years. So there's still going to be changes 100 years from now until we stop emitting carbon dioxide. And there's a number of things we can do there. And we also need to mitigate, which is basically reducing the amount of carbon we emit into the atmosphere. And we can do that by capturing it, or we can do it by using alternative forms of energy. So the UK is the only country that has a legally binding framework to tackle climate change. And as I've said already, I mean, this is all very good, but actually we need to basically, when we are reducing our emissions, but part of that is to do with the fact that we've exported all our manufacturing industries, etc., and we don't count those within our carbon budget. The Climate Change Act basically formed the Committee on Climate Change, and it required that emissions were reduced by 80% by 2050 compared to 1990 levels. And it also required that we basically did this thing called a UK climate change risk assessment every 5 years. And this is something I'm involved in this time, which this will be the 3rd time we've had a climate change risk assessment. And the key messages from the second risk assessment were basically that we have 6 priority areas that we really need to be thinking about in the UK. And you can see that a number of those are actually related to water. The top one is flooding and coastal change risks to communities, businesses and infrastructure. And then there's risks from heat waves, basically, to health, well-being and productivity. And then there's shortages in public water supply, agriculture, for agriculture, energy generation, industry. And then there's a number of other ones, basically, that are around food, natural capital, and disease, basically. So again, thinking about the difference in impacts between 1.5 and 2 degrees. Again, to remind you, we're going to reach it between 2030 and 2052. Basically, we're expecting a lot less extreme weather where people live. 10 million fewer people exposed to the risk of rising seas. This is just a kind of overall summary. But there are some things that will suffer regardless. So coral reefs are on the way out, basically. Putting it bluntly, they're on the way out. They're not, at the moment, I've got a couple of PhD students actually starting in September in a program that I'm running who are looking at trying to genetically modify coral to actually make it more resistant to heat. And I think that's a really good thing, because we need those type of people to be working on this to save coral, because coral is really sensitive to warming, and it's one of the first things and one of the most sensitive things in terms of risks from climate change. The other thing to say is something that James said right at the beginning, actually, when he introduced me, that basically when we look at the risks from water, heat, energy, food and land, the differences between a 2-degree warming and a 1.5 degree world, actually you can see here, this is the change in risk, yeah, at the bottom here, this is for 1.5 and 2, and this is from a study by Ed Byers. You can see actually this change really maps very well onto this vulnerable population, basically, in terms of populations living in poverty at the moment. So actually, I think that, I don't know, climate change is a really pressing issue, but poverty is also an incredibly pressing issue around the globe. And what you can say is that climate change will make poverty worse. So the already poorest people will suffer the worst from climate change, because the impacts are going to be largest there, but also because they don't have the money to actually do anything about it and to adapt. So we're perhaps going to see very large climate migrations as well as part of this, this warming. So we need to try and keep below 1.5, and to do that we need to basically go to net zero by 2050. We need basically unprecedented change in terms of scale and speed. And this, just to show you a little bit on the progress that has been made so far, you can see that 2 countries have achieved net zero so far. There's a couple of countries, Norway and Sweden, that in law they have to achieve it, Norway by 2030, which is great. You know, maybe we should be trying to achieve that too. UK now 2050, proposed legislation. Obviously it went through the Commons on Monday. It's supposed to be going through the Lords today. But you can see there's a whole load of other countries, including the EU, which can't decide what they're doing on this at the moment. It's under discussion, but there's a lot of countries that aren't in there. You know, it's 195 countries signed up to Paris. There's a lot fewer than that there. So we're in trouble. But in the UK, we've got this net zero report that was recommendation from the Committee on Climate Change, which, as I say, the government put it through the Commons on Monday. We've now changed our target to net zero, as long as it goes through the Lords, by 2050. I'm not going to go into what we need to do that, But I do have optimism, actually, and I mean, I was at this lobby today, and I have optimism for a few reasons. One, I think that there has been so much movement in this area since October, actually, really since people got behind, for one thing, the school strikes. Greta Thunberg is just an iconic image of her sitting outside in the cold and protesting every Friday. And now it's moved all around the world. We've got people gluing themselves to Parliament, Extinction Rebellion, which are direct action, and all sorts of other protests going on. More reasonable one today that I attended as well, in terms of talking to your MP and lobbying. I also attended this symposium. I was very fortunate to attend this symposium here, which was amazing, in basically the Arctic Circle in September, which was basically 2 scientists and about 28 people from the finance world, right? And it was really interesting because I learned a lot about acronyms in finance, but also because we had people like Michael Sheeran, who's the chief strategist at the Bank of England there, and until that point, actually, I was really despondent about climate change. But actually, when I went to that conference, I became a bit more hopeful that actually, even if policy wasn't going to do anything about it and politicians weren't, perhaps finance would just push them towards that anyway. So we've got people power and money power, yeah? Those 2 things together can perhaps change things regardless of political power and will. And so things like the top 300 companies have committed to basically carbon reduction targets, and the rise of renewable energies. And basically there's been a whole load of studies. There's a great picture, isn't it? I thought I'd include that one. Basically, looking at, even with weak global climate policies, we could produce 70% of world power from non-fossil fuels by 2050. Okay, that's not enough, right? But basically these are studies that look at these things. And another thing is, expect the unexpected. These rapid changes can happen really fast. These are the projections of basically solar power, and you can see that actually this is the reality here. Yeah, so it can all happen really fast if there's the will and the technology and the money behind it. So I think I've run over. I'm sorry, but I hope you found it interesting. So basically, just to say that, at the moment, we're on a trajectory of about 3.5 degrees warming, which is quite sobering. We already live in a 1 degree warmer world, and I hope I've convinced you that there's already many more extreme weather events. These will get worse, and I didn't even talk about sea level rise. We're not tied into 1.5, but we're going to be tied in very soon, within probably a decade. We can limit global warming, but we really need to be acting right now, and all acting on this as well. And of course, we can't do this alone in the UK. We need this buy-in globally, but we can perhaps start to show leadership in this area. I think we have shown leadership, certainly in legal terms, but perhaps not in actual terms, in some of the decisions certainly that have been made recently in government, including the one that decided to put VAT on solar panels yesterday in government. I do have optimism, actually, because I think that eventually we will force governments to take action over this. And thanks very much.
Well, that was a very good round of applause for, I think, a fantastic talk. There's a lot to mull over, and I'm sure there will be a lot of thoughts spinning around your heads. We have a bit of time, so if you have a question, we have 2 microphones. I would ask you to wait for your microphone before you speak so that everybody can hear, and then we'll get through as many. Please make your questions succinct, and the same with your answers.
I'll try.
Does anyone have anything to pose to Professor Fowler? I'll take the first one over there. I'll come to you next.
Thank you very much for a wonderful talk. Are your PhD students looking just at temperature rise in the sea, or acidity increase as well? Because that's also damaging to corals.
I mean, they're not my PhD students, actually. I'm running a doctoral training program, which is centred around climate change and impacts from the Anthropocene. So I've got a number of students starting, so I'm not supervising them because it's not my area. But as far as I understand, yeah, they're looking mainly at the effects of temperature, but other aspects as well. And the really cool thing is, obviously, they're actually doing this in reality. So they're growing these corals and changing them genetically and then trying them out in warmer water. And they're obviously enjoying snorkeling and things around coral reefs as well. We had a lot of people apply for those projects, I have to admit. But yeah, so they're basically seeing if it actually works in reality. So they'll be trying it in real seawater and things.
Which is more acidic than it used to be.
Exactly. So that's all kind of a given, yeah.
This one here with the tie and the pale shirt.
Thanks very much indeed, Professor Fowler, for a very interesting talk. I'm glad you were at the climate change event earlier on today. I was. I spent about 10 minutes haranguing one MP about the issue and what to do. But his question was, is there only one thing which he could take away? I don't think he's really listening to the rest of what I was saying, but is there one thing you could say to politicians which they really need, UK politicians, they really need to do?
That's a really hard question. No, I mean, I was talking to my MP earlier on today, and I think the one thing that they need to do is go beyond. Maybe it's not one thing, but it's basically going beyond agreeing to reduce emissions by 2050, but basically going into actually the nitty-gritty of how we're actually going to do that. You know. And I know that the government will produce a response to the Committee on Climate Change's Net Zero report. But if it's anything like their adaptation plan, which was a response to the Adaptation Committee's report on the climate change risk assessment, it will be really woolly and very, woolly. Just the wording is such that they can get away with anything, and there's no specific measurable objectives in there. And I think at the moment we need things to be really detailed and specific. And I mean, yeah, for me there's two main target areas: transport and domestic heating, and aviation as well. But I'm not sure they're going to be convinced by aviation. So I think first we need to be starting with those two things, and they need to be investing huge amounts of money in those things and subsidising them, because quite honestly people can't afford to buy electric cars. Public transport needs to change and become decarbonised and cheaper, and we need to change the way we heat domestically, because that's about a third of our emissions at the moment just come from domestic heating. That's probably the biggest sector. I know that wasn't one thing, sorry.
There's lots of hands going up. I think this one in the middle, then drop one at the back, and then I'll have you next. And then you. I knew it was going to be busy.
Thanks. Yep, so in your report, you showed the graph of the linear growth of the temperature with carbon, and we spoke before the talk about how the IPCC can't, they say in the report that they don't model non-linear chaotic things because they can't. So the question then is, do you think either the IPCC or some other body of scientists should do some publicly available work that talks about these non-linear things which could lead to abrupt climate change possibly within the next couple of decades, or we don't know, but someone should someone or some group be formed that does this job. It can't be bulletproof science because so it can't go in the IPCC report, or maybe it should. I'm just curious on your view on that.
Yeah, I mean, it's interesting because they put geoengineering in the latest report, which I've just read quite a few of the chapters for, and I wouldn't say that was bulletproof science either. But yeah, I mean, you're quite right that we can't produce, I mean, things like the methane release from permafrost, we really have no idea. We can say something about the observed rate, perhaps. We can measure it to a certain extent over certain areas, and people are doing research on that. But we don't know whether there's going to be some kind of, massive melting of permafrost and how that's going to then feed back into the climate system. The other interesting thing is ice dynamics. how will that affect albedo in the northern hemispheres? There aren't dynamic ice sheets in climate models. And also cloud feedbacks, clouds at 50, 100 kilometre resolution, not really well parameterised in a model. And a lot of the most recent models suggest that we might be seeing even warmer temperatures in the future because they've got better cloud schemes in them. I think that there needs to be discussion of these type of things, and I think there has been discussion in the past, but we haven't come up with quantitative numbers. So there was sort of an expert judgment type paper that came out on tipping points, which is part of the reason they decided on the 2-degree threshold in the first place. If you kind of backtrack to all of those papers about dangerous anthropogenic climate interference, it was called, in the climate system, interference in the climate system. There was a conference in Oxford, I think, a decade ago now, or something, where they looked at some of these things. And you're right, it might be time to revisit.
Do something new.
Yeah,
Okay.
yeah.
Thanks.
Question far back there, just in front of the box.
You acknowledge that the role of human population has a part in this whole matter, but it didn't appear anywhere in those lists of ambitions or aims to bring about a remedy to the problem. Why do you think this is so, and would you agree that what is required on the individual level is a really big change in behaviour? Just to give a very quick example, where individuals installed solar panels in Germany a few years ago, it was noted that because they had access to cheaper electricity, they then installed air conditioning in their homes. Thank you very much.
Right, okay. I mean, yes, I didn't talk about population. I mean, I'm a scientist, basically. Yes, population has a huge impact, obviously, growing populations, because people then use more carbon, because everybody has an individual carbon budget, I guess. And then obviously puts pressure on other things as well, as you saw in the Indian example at the beginning there, in terms of water and all sorts of other things, food, etc., etc. We've got finite resources, and we're using 2 times the planet worth at the moment. So it's unsustainable in the long term. In terms of, I don't know, I mean, we can't just be thinking, it has to be a behaviour change, so if you're the type of person who would put in solar, you would then hope that you're the type of person who wouldn't then install air conditioning. But then, if you're only using your solar and it's all renewable energy to drive your air conditioning, then that's surely a good solution. And it's perhaps not a long-term solution, but perhaps we do need more air conditioning in certain parts of the world. But if you can actually drive that with solar, then that's a good thing. I mean, the same thing might be said for solar-powered desalination plants. And they have a lot of these things now, not desalination, but actually water treatment in developing countries, where you can actually treat water very quickly with solar-powered water treatment. So people can actually drink clean water, and they're getting the energy to clean that water from solar. So you can see some of these really cool technologies coming on board, and I think if we can do it with renewables, then yeah, why not make people's lives better?
I have many more hands gone up than I have time for. I've got just 2 more questions. I have you in the jacket and you in the brown shirt. I'm sorry for you and you. However, I will let you know Hayley's not running away.
No, I'm here afterwards.
And we'll be here for a good half hour yet. So informally, you may pursue.
Thank you. Do you have a view as to the effect of, or the percentage effect of man-made global emissions, energy and carbon emissions causing climate change, as opposed to the natural cycle of global warming and cooling? If the whole world got to 0 emissions, would there still be a danger of further climate change, or will we be on a plateau?
You'll still get, I mean, because of the lag in the climate system, because you basically have carbon dioxide staying in the atmosphere for 100 years, you would still see warming, yeah, beyond net zero, if you like. So we're talking about 2 degrees or 1.5 degrees by the end of the century if we get to net zero by 2050. But the other thing we need to think about is sea level rise. So sea level rise is an even slower response. You know, so basically the ocean warms at a much slower rate. So actually that would continue to rise probably for 300 years or so beyond when the atmosphere stops warming. It's a really lagged effect. So I can't remember what the rest of your question was. Sorry, what else did you ask me?
If we stop emitting now, are we at a plateau, or is it going to get worse?
Well, I mean, I'm sure there was something else you asked as well, though.
To what extent is climate change due to man-made emissions?
Yeah,
to what
whether
extent is it occurring naturally in the order of things over centuries?
Okay, so I mean, we'll still obviously see natural cycles. So, you know, we'll still see El Nino events, for example, which cause big peaks in temperature because basically the event releases a whole load of heat from the ocean. So we'll still see things like that. So we'll still see those types of variability. We'll still see solar variability. At the moment, we should be going through a slight cooling period because of solar variability, but actually we're not. You know, it's masked by the warming. I expect the warming will probably still mask that solar variability, but you'll still see little. I mean, you still see variability. Yeah, it may even it's going to be enhanced, if anything, by the warming.
Very quickly, please.
Thank you. Are you fearful of the impact of geoengineering and the pressure that the Americans probably are putting into that rather than doing anything about the cause?
I did a whole debate on this as a Pint of Science event the other day, actually, or a few weeks ago. You know what? I've changed my opinion about geoengineering. I worry that we will just jump into it without thinking too much. Yeah, I mean, for those of you who don't know what geoengineering is, we're talking about crazy things like giant mirrors in space to reflect solar radiation back. We're talking about putting sulfate aerosols into the atmosphere again to basically act like acid rain, to basically reflect more solar radiation. We can do other things as well. There's vast variety of crazy things we can do, but they're called geoengineering because they're on a planetary scale. So, I mean, I used to think these ideas were crazy, right? But when you go back to this gentleman in the middle here and you start to think about some of these possible runaway climate effects, actually, I think it's a good idea to do research into how you might implement them and what effects they might have. Because what my worry would be that we would suddenly enter some realm of basically a runaway climate effect. And we'll then be in the situation where, somebody does something crazy without knowing what the potential effects might be. Or two, we're in the situation where we can't do anything about it because we haven't basically looked at any of these technologies and we can't get them together soon enough. It might give us some breathing space. I mean, it's really interesting actually the way it's being talked about at the moment. I still worry about it being used. It can't be used though as a sort of an alternative to reducing our carbon emissions, because the problem is that as soon as you stop geoengineering, you have this massive bounce back. You know, in terms of, well, you won't mask that warming effect anymore.
We'll have to draw a close there because we have the very important thing happening next, which is a glass of wine next door, and I know I don't want to delay any of you for that. I would love to thank you all for attending and listening so attentively to Professor Fowler's talk and for such a good set of questions. We have a number of interesting events at the Society. There are two I'd like to draw your attention to. The next public lecture, which is the same format as this, is on the 25th of September on what individuals can do to achieve healthy ageing. And if any of you, like me, are ageing, I would expect you all to be here for that. And on the 2nd of December, we have another climate change event, which will be the fourth one in this year's series of climate events, which will be about climate change and the livestock sector. But before I dismiss you all from this excellent event tonight to our social next door, I would like to present Professor Fowler with a certificate of gratitude from the Society, and I'd invite you all to thank everyone.